Alright friends, we will start with another recorded video where we will analyze the second case when bridge is just outside transition of curve. We have a bridge which is bridge 3 at a down in Utratiya Sultanpur section. This is a downline bridge on Kadunala. There is a nala named Kadunala and this is downline. This is increasing kilometer, this direction. So this is A2 of the bridge abutment A2, this is A1 of the bridge abutment A1, and as you can see in increasing kilometer outside the abutment there is slight kinking in the direction of the track. So the track is like this, but it has kinked here, K-I-N-K-E-D, kinked here, as can be seen in this photo also. This is the photo of the left rail, this is the photo of the right rail. Left and right are with respect to person standing and looking towards increasing kilometer, like towards this direction. And this is the same photo taken from about 150 meter outside the bridge. This is A2, this is A1, this is increasing kilometer, this is TTP1 of the curve. TTP1 of the curve is approximately 78 meters ahead. So from TTP1 we have to go behind -7 station, that is -70, and then further 7 meters more, that as we will see, and then we will reach the CH line, this channel sleeper, last channel sleeper of the bridge. This the curve, there is a curve of 13 stations and the name of the curve is 20 down. Transition length is 30 meters, so 0 station is TTP1, station number 3 is CTP1, station number 13 is TTP2, station number 10 is CTP2, and in the total station data we have surveyed, this is A1RR, right side rail. RRR refers to repeat of the data and it has been repeated 3 times. The last channel, in fact first channel sleeper, and the data is inner edge of rail head, as was the case in earlier video. Let me just show it again, the photo. This is inner head of rail, inner rail head, inner edge of rail head, and the trackman places his thumb here, and at the edge of the thumb and at the edge of the railhead is the we place the pole, we place the prism pole, and then this prism pole is observed from total station. So the data, the XYZ coordinates that we get are of the inner edge of the rail head top. So again, going back to our case study here, the case is bridge 380 down, and these are the videos. So train will up, since it is a down line and increasing kilometers this direction, so train will approach from here like this. Train will come like this, train will come like this and this. So what is happening here, as you can see here, there is a kink. A2, the last channel sleeper, is somewhere here, but the kink observed is somewhere here, and here there is a rail joint. Actually there is a 1 meter plate and there is a rail joint, and it has pushed because of the centripetal force, you can say, or because of the force of the wheel gauge face. It has pushed the track, and this rail joint is somewhere around 7 to 10th channel sleeper, and it has pushed it in our side of view, right side, or with respect to increasing kilometer it has pushed to left side. So this is also an error, and this has happened because our approach track is misaligned. And we can see that the TTP1 of the curve, which is approximately 77 meters ahead of the A2, and that is abutment 2 of the bridge, is misaligned towards right. With respect to increasing kilometer, if we say the direction, this is misaligned towards right. That is to say, a man is standing here and looking towards increasing kilometer. So we will see, as can be seen here. So this is A2, this is another view. The person is standing on the bridge and looking towards increasing kilometer. This is A2, abutment A2 of the bridge, and we see that the curve has moved outwards, moved towards embankment, or rather we can say the curve has misaligned towards right. And if we see towards down, towards decreasing kilometer, let's say, let's make it decreasing kilometer. Let's change the direction to this. So if we look towards decreasing kilometer, the track is found to be straight. The approaching track is found to be properly aligned. As a matter of fact, there is a reverse curve here also, one curve like this, then like this, but it is visibly straight, visibly aligned. But if you look towards increasing kilometer, it is visibly misaligned. So this is our introduction from the photo. These are the side photos. Now let us get back to our AutoCAD data. What we have here is, this is A1, that is abutment A1, and R. Actually there are 3 points we have taken: A1R, and then A1 double R, and then A1RR. So actually what we have done, we have taken 3 points here, because this will guide our alignment actually. Okay, the first channel sleeper, rail head inner edge data of the right rail we have selected in this case. So all these values refer to right rail actually, and we have taken data up to station number 27. So going back to Excel file, we have data till station number 27, where station number 13 refers to the end of the circular curve portion. Alright, and -7, and then this is like, so we have let us first see what is the actual distance. Let us first draw the approach alignment. So since we have taken 3 readings for the first channel sleeper, we will select the middle of the 2 readings like this, and then we will draw it along, and we will select the one which is near about middle, so this one. So this is our approach alignment, and this is our approach alignment. We will extend it further. Let's draw another line here, and we will extend this approach alignment beyond station number 27 for our purpose. Now what we see, first of all, this is the first thing we do. First thing we do is we draw the approaching terminal tangent alignment. Okay, this is the terminal tangent, or rather first terminal tangent, and this is A2, that is the last channel sleeper of the bridge. So first channel sleeper and last channel sleeper data defined our terminal tangent. Now let us directly go to station number 0, which is here. This is 0, that is TTP1. This is 0, that is TTP1. Alright, so what is the misalignment here? We see the misalignment is to the tune of 150 mm. Misalignment is to the tune of 150 mm. Alright, misalignment is the tune of 150 mm at TTP1. So this TTP1, that is the starting of the curve, which was supposed to fall on the same line on which the terminal tangent should be, is actually 150 millimeters, as in this figure, right of the actual alignment, the correct alignment. That is to say, we can see in this photo, this is the ideal alignment, but the TTP1 of the curve is, this side, 150 mm this side, and we need to slew it 150 towards right in our view, or with respect to increasing kilometer, we can say 150 mm towards left. So we will draw this data, we will fill this data as we go about solving this problem. one by one. So right now everything is blank. This channel last is the good point. We will insert another row here, and actually channel first will also be our good point. Actually first channel sleeper is also our good point, last channel sleeper is also our good point. And using these two good points, we draw a straight line which gives us terminal tangent alignment for the first terminal tangent. Now as we had seen earlier, we can use the upload command and we can upload list file, that is a auto list application source file, which is basically a kind of plugin. The name of the plugin is FSPI. We can load it, and after loading we can use it to draw the curve, the circular curve with transition in AutoCAD for any desired radius of curvature and any given length of the transition length. But for that we need two terminal tangents. So one terminal tangent we already have, which is the best suited for our case, because we have chosen the last channel sleeper as our terminal tangent, because we, for our present analysis, we assume that we are not doing any slewing in the bridge. That is to say, there will be no slewing in the bridge. Bridge will remain as it is. Only the approach track will be slewed or corrected to correct the alignment. So as we can already see, we already have an error of 150 mm at the TTP1 of the curve, and let us also feed one more data in this, that is the data of the OHE. This is the data of OHE, distance of upline track center from upline OHE. Sorry, this is a mistake. This is actually down. Let us go back to Excel file. This is distance of down track center from down OHE in mm. So this is IMP when it was installed, and this is before slew. IMP means when the track was opened at that time, what was the distance of OHE, and this is the distance on the day of the surveying. This was done somewhere, the survey was done somewhere in September October 2023, and using the distance as 2800 mm as the minimum required distance, what is the margin of slew that we have? So before slew, as you can see, the distance like station number -1, which is almost near the TTP1, the OHE is 952/2, and it is 4.8 meters Sultanpur side of station number -1, which is very near to, or we can say 5.2 meter LKO side of station number 0. So it is almost near TTP1, and IMP was 3.08, but currently its distance is 3.120. And if we use 2800 as an mm, so there is margin of slew of 320 mm here, and what we require is 150 mm. So we can see that the parameters match. If we slew it by 150 mm, our OHE distance will still remain more than 2800 mm. Likewise, we have OHE number 952/4, which is near station number 4, and margin for slew here is 200 mm at present, on the day of survey, and we will see what we get in the so let me put this data also in the Excel file. So we have surveyed only till station number 27, and station 27, and we have this data nearest curve station number till 20 only. So either way, I will put this whole data into Excel for reference. So I will add one more slide. All right. So we have this data of OHE and chainage. Okay, for reference. Now let us get back to our AutoCAD file. So we have this first terminal tangent, and according to first terminal tangent, the TTP1 of the curve is supposed to be 150 mm left. That is to say, to correct the alignment, we have to slew this point 150 mm towards left. Again, left and right are always with respect to increasing kilometer, direction of increasing kilometer. So the person is standing here and looking towards increasing kilometer, somewhere looking towards this direction. And according to that, this point needs to be slewed. This point needs to be brought here. So the slew is towards left. Okay, the person is standing here looking towards this direction. So the required slew is towards left, and that is what we will enter here. So we will use two ways to solve this problem. First is correcting only transition portion, in which we will use AutoCAD data from for TTP1 and up to CTP1 actually. So station number 3 is our CTP1. Let me rename it here 0 underscore we have to edit it. Alright, 0 underscore TTP1. Okay, 0 underscore TTP1, and station number 3 is our CTP1. So 3 underscore CTP1. And further, the station number 13 is our TTP1. Underscore TTP2 actually, sorry, TTP2, and our station number 10 is CTP2. Our station number 10 is CTP2. Underscore CTP2. Alright, so we have named the terminal tangent point, circular tangent points, both sides. We already know the first terminal tangent. Now for the purpose of our analysis, what should be the ideal tangent, the second tangent, where should it be? So there are many options for that. The first option that comes to our mind, that should come to our mind, is let us take the farthest point that we have, that is station number 27. And let me again clarify that these stations, that is station number 27, 26, 25, that is to say all stations starting from 13 to till the data we have taken station 27, they all come under straight portion of the track. Although after 27, somewhere around 28, 29, 30, another curve starts, which is the second part of the reverse curve. So for our analysis, we can select, let's say, station number 25. Let us select station number 25 as the okay, let us do one more thing. Let us see whether they are actually on a straight line. So let us draw station number from 27 to 13. Let us draw a straight line and see whether all the intermediary stations fall on this straight line. Alright, so let us see for example 25, what is the distance? It is 11 mm, not very large. 11 mm is kind of acceptable. 23, this will be something less actually. I think this is only 9 mm. Let us see station number 21. This is 17 mm. Station number 19, it is even more. It is probably somewhere around 27, 26 mm. So you see, see what is the exercise. We since the curve is already disturbed, and we can see that the TTP1 is not where it is supposed to be, it is very likely that the TTP2 is also not where it is supposed to be. because this has happened because of our overlooking the overall approach curve during the tamping by machine. And in every tamping, what has happened is basically in every tamping, machine has stamped it outside, outwards, 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 and so that is why the track has disturbed. So it is logical to say that the TTP2 is not actually at the right position. Now what we do, but we need to draw a second tangent for the purpose of our analysis. So that will be needed for our second part, that is redesigning the whole curve. Right now we are concerned only with the the first part, correcting only transition. For this we don't need to draw the second tangent, so let us, for the time being, not delete it, let it be there. We will solve it. Let us first find distances at every station. This is -1, and the slew required here is 124 mm. This is -2. Slew required here is, let us see how much is the slew required. Slew required here is 90 mm. Slew required at -3 station is 66 mm. Okay, let me pause it. I will calculate, or I will do all the calculation and then restart the video. Okay, so I have calculated these values. At TTP1 the slew required is 150 mm, then at -1 124, and likewise at -7, which is the nearest station to our bridge, the slew required is 13 mm. So first we will fill all these data in Excel. Alright, so here aligning transition points to ideal tangent alignment, that is A1 to A2. What we required here is slew to left. All the slews are towards left. So M7 is 13 mm, M6 is 30 mm, then 39 mm, then again 39 mm, then 66 mm, then 90 mm, 124 mm, and 150 mm. Alright, again, but this is not complete here. There are many ways we can work it out depending upon the time we have to analyze. We already see that the slew required as TTP1 is more than 50 mm. Okay, so right away, without going for the y ordinate analysis, we can let's say copy paste here, Control C, and stage 1 tamping here, slew to left, Control V, and 13, 30, 39, 39, and now we take it 50, 50, 50, 50, because 50 is the maximum, 50 is the maximum slew our tamping machine does in one round. And then from 50 here we can gradually decrease it to 0, either or at the 13th station, or maybe go further in the straight portion somewhere like 19 or 20. 20th station is here. So if we decrease by 3 points, so it will cover in 17 stations somewhere around here. So we can decrease it to 47, 44, 41, and like that. The required slew we can get 0 somewhere around here. Alright, 0, 0, 0. So this is one way. Okay, because first stage of tamping we cannot do more than 50 mm. So we already have a solution. Okay, we already have a solution just by AutoCAD analysis. Since TTP1 is more than 150 mm is required here slew, so we go by this first tamping. But let's say we go further till CTP1, and then we also use the criteria of y ordinate. We will get more slew here. So what will happen is we use the formula here. In this case, our L is actually 30 meter. Radius of curvature is actually half degree, so it is 3500. Rest everything is same. So For this value, the y coordinate formula for TTP1 will be 0. For station 1, we will use R equal to 3500, L equal to 30 and X equal to 10. So if we solve this in calculator, we will get, let me solve it in calculator. Let me use our own calculator here. So you can also see how what I am doing. So 10, X equal to 10, 10 cube, that is 1000 divided by 6 divided by R, that is 3500, and divided by L, that is 30. So we get 0.015. This is in meters, so 1.15. So it is basically 2 mm. So we get 2 here. Then again, let us solve it for X equal to 20. 20 cube equal to 8000 divided by 6 divided by 3500 divided by 30. So we get here 12.6 mm, which is basically 13 mm. So we get 13 mm here. And for CTP 1, which is the third station, which is the circular tangent point, first circular tangent point, we use small x equal to 30. So this value here, let us 30 cube is equal to 27000 divided by 6 divided by 3500, which is the radius of curvature, and divided by capital L, which is the length of transition. Here we get 428.428, that is 43 mm approximately. So this is 43 mm. This is to say, like I had said, we already have a solution for first round of tamping, because the first round of tamping is not going to be more than 50 mm. But let's say we go further and now solve it up to CTP1. So correcting only transition, we can either correct up to TTP1, or we can either correct up to CTP1, or if we redesign the whole curve, we will go in this slide, we will redesign the whole curve and how to do it. Let us first see here. So TTP1 needs to be slewed by 150 mm to left to align it to A1, A2, and as per y ordinate, it is 0. So 150 plus 0 is equal to 150 only. So if we take into factor both these, so this is the heading here, reline transition points after factoring in y ordinate of cubic parabola. So slew to left, this will be copied here, and here actually we have 150 plus 0. Again, y ordinate of cubic transition, in our figure, as we can see, when our curve will start, y ordinate will go above, or rather say left side of the terminal tangent. That is to say, our tangent will be something like this. Okay, this is a straight portion, then transition portion, the track will go something like this. So the values that we have, let us first find this offset values with respect to terminal tangent for stations up to CTP1. So we see here, this is 157. So that is to say, to realign the CTP1 to terminal tangent, we need to slew it by 157 mm to left. So let us fill here 157 mm. But on top of it, since it is inside the transition portion, or rather at the end of the circular portion, it needs to be 43 mm offset. There has to be 43 mm offset from the terminal tangent. So total slew required to actually make it a proper curve will be 43 plus 157. So this will be equal to 157 plus 43 equal to 200 mm. Likewise, we already have the y ordinate values for station number 1 and station number 2. Let us see what are the values for aligning with respect to ideal transition. So in case of station number 2, we have this value, that is 166 mm. So station number 2, 166 mm, we need to slew to left to align it to A1, A2, but we also need to slew it further 13 mm to make it a proper transition curve. So this will be equal to 166 plus 13 equal to 179 mm. And let us also see for the station number 1. Station number 1 needs to be slewed by existing position of the station 1 needs to be slewed by 163 mm towards left to realign it with the terminal tangent, but then we also need to slew it 163, but we also need to slew it because it is first station inside the transition. We also need to slew it by 2 mm more. So overall slew required to align it, or rather to make it proper curve, will be 165. 163 to 165. So now we see we have this solution, and that completes our question, or rather that completes our analysis here, which is the corrective only transition. So maximum slewing is 200 mm, and here it is 50 mm. So there are many ways to go about it. Like we can reduce this 200 mm slewing, which is at CTP1, and from CTP1 to CTP2 there are 10 stations, that is 100 meter. We can reduce it by 10 mm, then we will go up to 23, or we can reduce it by 20 mm. So we can reduce it by here, but that assumes that TTP2 is actually at correct position. So the stage 1 tamping that we have written here is already correct actually. What would be our stage 2 tamping? Stage 2 tamping would be, let us say, required lift is another context. Required lift has to be found by using let's insert, or rather let's copy and then insert, and let us name it remaining slew. Alright, so remaining slew will be slew to left equal to this minus this. Remaining slew here is 0. Alright, and 159. This is remaining slew. I am calculating for the second stage. For second stage we can go like this, 0, so 0. All these are 0 actually, so let us copy paste from here, Control C to Control V, 0 X, Control C, and let us paste numbers. Alright, but since we cannot slew more than 50 and here required is 74, so we will go here 50, again 50, again 50, and we have to go more than 50 because here it is 118, 123, 159, so again 50, then again 50, and then we can again taper out, reduce it to 3 values. Let us reduce it by 3, 47, 44, 41, and let us see where it will end, somewhere here. Alright, it is 0, enter 0, enter 0. So this is our second stage stamping, this is our first stage stamping, and this is our second stage stamping. Alright, now again let us copy it and let us insert copied cells, and again this is remaining slew. And what will be the remaining slew? Remaining slew will be, because we have slewed these two values and overall slew required was this actually, so remaining slew will be equal to this minus this minus this. So this is the remaining slew. We are going only up to CTP1, so 109 is required here. So what will be stage 3 tamping? Stage 3 tamping, let us paste here, paste number only, and so we cannot slew more than 50 mm in one stage tamping, so this will be reduced to 50, this will also be reduced to 50, and this will also be reduced to 50, and then we'll again taper it down like this. Okay, 3 mm like this. Alright, this is third stage stamping, and for fourth stage stamping we can again use the same method. The remaining slew will be equal to, total slew required was 13 here, minus 13 already done, minus 0 already done, minus 0 already done. Alright, so it is 0, and then we go up to here, so minus 59 is the maximum slew required here. We may use it 50 only, and then again taper down to instead of 59 we slewed by only 50 and then taper it out 3 mm at every stations. So these are 4 rounds of slew, and in 4 rounds of slewing we have corrected it using only the correction of approach. Alright, and what was the total slew done? So remaining slew, in the remaining slew itself, this is actually 4th stage slew. Alright, this is 4th stage slew. Remaining slew was actually minus this, minus this, minus this. 59 only, but we have used only 50 at the last. And if we want to see what is the total slew done, the total slew done was actually, this was the actual total slew, and this equal to this plus this plus this plus this, so 179, and then we can draw it down up till here. So we see the total slew also. And to see the criteria of OHE, because we saw that this OHE is near station number -1, then this OHE is near station number 4, where margin for slew is 200 mm, station number 4, near station number 4, and actual slew that we are doing is 179 mm at station number 4. So this is within the permissible limits. So this is an acceptable solution. For station number 10, the margin of slew was 120 mm. This margin is taken when we are slewing the track towards left, okay, because when we will slew the towards left, this value will reduce, this distance will reduce. Let me clarify that the OHEs are placed this side. OHEs are placed at this in this direction, or rather along this direction. So when we move the track towards this, the OHE distances reduce. So when we move the point 3, station number 3 towards this, the distance from the OHE will reduce. So at station number 4, the nearby OHE is 952/4, which before slew it was distance 3000 mm. Margin for slew is 200 mm, because if we slew 200 mm towards left, it will reduce to 2800 mm. But actually we are doing slew at station number 4 only by 179 mm. So this is acceptable. So this solution overall is acceptable solution. We will have to run the tamping machine 4 times. For first run this, second run this, third run this, and fourth run this. As you can see that we are slewing the track ahead of the TTP2 also, like this portion goes ahead of the TTP2, and these all portions are slewing. The slewing is happening ahead of the TTP2. This is acceptable, number 1, because we already know that the curve number 13, station number 13 is not actually at right location, and we can see the versine data also. What are the versine values at station number 14, 15, 16, 17, 18, 19? We have gone up to station number 21. Alright, and this was supposed to be in a straight portion, but there have been some slews, overall slews like this, 59, 47, 35. But if you analyze, you can do more analysis in this. Like, let's say this is the total slew that we have done. This portion has been calculated mathematically, and then this portion has been corresponds to the linear tapering. Alright, this corresponds to linear tapering. Again, let me repeat, this portion from -7 station to CTP1 has been calculated mathematically, of which TTP1 to CTP1 part is calculated by cubic coordinate formula, y ordinate of transition, which is a cubic parabola formula, and these points have been this information has been found from AutoCAD with respect to the ideal tangent alignment A1 A2 of the bridge. Adding these two, we have got this, and then this tapering has been linearly tapered out. There are many options like linear tapering. We have reduced by 3 values. we can, instead of reducing by 3 values, we can reduce by 2 values. So we can do more trial and errors in this, and we can also find like this is the total slewing, and if we hide this, let us hide this, and if we draw a column which with name starting versine and final versine. So we can we can do more analysis. We can create a column for starting versine, we can create a column for final versine, and if we have the values of versines that we have correctly, the versine should be correct actually. Don't use for versine, let me show one more thing here only. Either use the alright, so many times there is versine kit is not available, so there is no way to create proper offset, because if you don't take proper offset, the 20 meter thread may touch the rail at some places and the versine that you calculate at the center will be incorrect. So for that you can use two bolts of same thickness like it is placed here, and so this will be the offset, and since the both nuts are same, the offset at the two terminal station will be same. And what is this offset and what is the value you get at the center of the thread, the difference will give the proper versine. So you should calculate the versines correctly, and let's say if you have the starting versines or the versine, surveyed versine, let us say surveyed versine at survey, versine at site, let's say versine at site, and what will happen to versine after slewing. So versine, so if the slewing, these are the slewing values and you already have the versine, initial versines, you can find the versine after slewing using the formula of the simple that formula is called let me just check what that formula is called. Yeah, that formula is basically based on, if let's say versine at TTP1 here, let's say it is 5, alright, and you slew it by 150 mm towards left, so it will increase by 5 plus 155, but the neighboring stations like station number -1 and station number 165, these two have also been slewed to left. So when it is slewed to left by 124, it will reduce the versine at this station by half of 124. Likewise, when this point is slewed by 165 mm to left, the versine value at this station, the center station, will reduce by half of the 165. So what will be happen is this minus and then bracket 124 plus 165 and then bracket close and divided by 2. So this will be the new versine. I hope you get my point. Versine at site was 5. I am just giving an example, and you can do further analysis about accuracy of your work that you are going to do. Right now I have the versine at site, but it will take a lot of time, so I am giving just example how to calculate versine after slewing. So if initial versine was 5, you have slewed that point, that station which is station number 0 by 150 mm towards left, and station number -1 and station number +1, which are the neighboring stations, you have slewed these two also by 124 mm to left and 165 mm to left, as you can see, slew to left. So this will be the effective formula: 5 minus 150 minus 124 plus 124 sorry 5 plus 150, because no, there is a mistake, I'm sorry, this will be actually 5 and it will be minus actually, because it will be minus and here it will be plus, minus 0.5. okay, this is simple mathematics, simple triangulation actually, and there is technical name for it, I'm forgetting it. So I will make it in next video. What the technical name is, basically simple. This is concept of similar triangles. Okay, concept similar triangles. Let's say here it was 4. Let's say here it was 7. Let's say here it was 3. So what will happen to these values? So these are the changed values. Okay, this is 1.5, this is 0.5, this is 12. So likewise, if you already measure versine at site also, and again it has to be measured correctly, you either use the versine tool or you can use a nut, 2 nuts of the same dimension, same thickness. Then you can see, you can calculate versine after slewing also, and you can compare this versine after slewing, how ideal it is. The station to stations variation should not be very much, should not be too large, and accordingly you can determine the efficacy of your solution, whether you need to, the reduction that you were, the tapering that we were doing was for 3 millimeters at every station, whether it should be done by 2 millimeters, or if at some locations the station to station versine after slewing is a little large, we can make some variations in the overall slew to correct it, to correct the versine after slewing, to make it more acceptable. And accordingly, if the total slew is changed, stage 1, stage 2, stage 3, stage 4 tampings values will also accordingly change. So this completes our analysis for bridge 380 down, Kadunala Bridge, and using the concept of aligning the transition points to ideal tangent alignment, and using the y ordinate of transition cubic parabola formula, y equal to x cube upon 6RL. Next, we will see how to redesign the whole curve. In redesigning the whole curve, we already have the first terminal tangent, which is A1 to A2, the line that is following along the A1 A2. We will need to determine the second tangent, and this was the exercise that we were going to do. We will continue it in the next video. There may be many options of selecting the good point for the second tangent. We may select 27, we may select station number 26, we may select station number 25, and what will be the second point which we will join. So we will see that in next video.